doom, doom. Now, okay, good. All right, so let's get back talking about music. Specifically, last time we were talking about string instruments, I believe, if I remember correctly, but it's a long time ago. I'm looking at the live stream, it's like 3 weeks ago. And even though you've had some written assignments, you might not all be all totally on top of this. Hey, Konstantin. Okay, so just a reminder of where we were last time. We talked about a string. We said, okay, here's a string. Good. And it's kind of like a guitar string or whatevs. And we said, on this string, there's going to be a wave that's going to be on the string. And we had certain things we said, okay, like the length of this thing is L. Okay, ooh, that is really nice marker. I'm excited about the marker. That's cool. So, and we see that the string is fixed at two ends. You see kind of here and here, okay? So when we pluck this string and let it oscillate, okay, certain oscillations are possible, certain oscillations aren't possible, and specifically the end points need to be fixed. Does that make sense? Like you can't have at this point and this point motion of the string because the string is tied down, okay? So let's think about what kind of oscillations are possible for this string, which would be standing waves. A reminder, we talked about standing waves a long time ago when we did the slinky on the ground. And remember that? We like oscillated the slinky back and forth, and the slinky was kind of displaying a certain pattern. That was like in March. You remember that?
Yes.
Yes, thank you, Finton. I almost fell asleep there. Nice. So, and what we saw was we saw a certain number of bumps as we were kind of wiggling this thing back and forth. So let's think about the kind of patterns that could show up in this thing in terms of bumps showing up, but the ends being fixed. The simplest way that we can have that is to have just one bump, okay? So we could have a string like this, and here's kind of the undisturbed situation, and we could have that string kind of oscillate back and forth between these positions, kind of like this. Wow, that's like almost like animation. That's so cool, okay? So the string is oscillating. That's, I'm really learning how to do it. Not this bad. Okay, this is good. So the string is kind of oscillating back and forth. We're just kind of imagining that's kind of what the string looks like as it's vibrating back and forth. Does that make sense? Okay, I'll pretend you said yes. Now, riddle me this. What is the wavelength of this wave? Oh, it's not showing up, right? Okay, the length of the string is L, and this is what we see. We kind of took a snapshot with our iPhone. We imagine we have an iPhone, okay? So, and how much of a wave are we seeing there? Not everybody at the same time. I'll call on somebody. Ellie.
Huh? Sorry, what?
Okay, I'll call on somebody else. Alicia.
Half.
It's half a wavelength, right? So L is equal to half a wavelength. So how long is the wavelength compared to L?
2L.
2L, that's right. So in this case, we would say, okay, we're going to write it like this. Lambda 1 is equal to 2L. I'm going to write it up here so the Germans know what's going on. Be aware, I wrote it higher up for a specific reason. We'll see in a minute why. Okay, you guys ready?
Yes.
Okay, good. So now we're going to say, all right, well, we could have done that. But we could have also had a situation where instead of having one bump, we had two bumps. How about that? And the wave is kind of oscillating back and forth like this. Okay, so
that's crazy.
That is kind of crazy. And I'm going to turn this thing sideways for you so I have a little more space. Uh-oh, I don't know who's coming to my door. Maybe it's Amazon. Sophie, can you open that? Is that far enough away? Whoa, this might fall off the table. That would be exciting. Okay, is this far enough away? I don't know. I'm gonna need more space. You're getting a tour of the apartment, not quite. So there we go. All right, you guys ready? Okay. If I need some space, I need to see more room here. So the idea is, the first wave we have was kind of like this. Yeah?
Yeah.
And the second wave is kind of like this. You have one up, and you have one down, like that. And it's going like this.
Yeah.
Right? So the middle is not moving, like that's me, and the ends are not moving, but there are two bumps moving otherwise. Okay? So that's kind of the wave we're looking at right there. And the question that we have to answer, well, we don't have to answer it, but we will. How long is the wavelength here?
4L.
4L will be wrong.
Oh,
Aw, don't be
Okay.
sad. Who was that?
Jacob.
Hey, Jacob. So tell me,
Belgium?
how much of a wavelength do we have here?
Maybe
Or
it's
type
one.
of-
One.
It's one wavelength, so one wavelength
Yeah.
is equal to L. Make sense? Okay,
Yeah.
now watch out though. I'm gonna write it weird again. You ready? I'm gonna write it not here, I'm gonna write it up there, kind of like I did there. Why?
Because
You'll
we'll have
see
to
in just-
divide.
Yeah, we're gonna show that in just a second. And the next one will make that clear. Let's do another one. This is gonna be super fun. My idea of fun is so weird. Okay. We have the length again, and this time we're gonna have 3 bumps. So we're gonna set this thing up and say, okay, well, we could also do this way, right? Yeah, so there are 3 bumps oscillating back and forth, just reminding you of kind of what the slinky looked like. So we had a situation where in each case, the ends are fixed. We talked about that, right? And these things, BT dubs, are called nodes. That's where they are not moving. But we also have, oh, color. Let's do red. Why red? Because it's not moving. That makes sense, right? Red, red, red. Is that showing up? Do I need to first erase it and then make it red? All right, good enough. This is also red here. The ends are nodes, but they're also nodes here, where it's not moving. Is that making sense?
Mhm.
All right, cool, sweet. There we go. Nodes are here, and then we'll just do, oh, we can do this. There we go. Here we go. All sense. That's a pretty messy diagram. I think we should do some more dancing. What do you guys think?
Yes, please.
Yes, please, more dancing. Okay, we're gonna move this thing over here so I have some space. There we go. All right, I'm gonna back up again. Just a reminder that the first one, yeah? On the first one, we said it was kind of like this, just like this. This is just one bump, okay? And now we said we had, whoa, I'm Spiegelverkehr, that's what's going on here. Okay, so this one, okay. Oh, I can't even, I'm stupid. Okay, this way. There we go. I'm adjusting the wrong hand. Oh, I'm going the wrong way. There we go.
You have to go to American Got Talent. This is immaculate dancing.
That's the 2. You guys ready for the 3? This is kind of difficult. Do not attempt this at home. Okay,
Oh,
so
I
we
thought we
need
were
3
trying to
bumps.
imitate you. Okay.
So we're gonna have to use like my torso as a second bump. Okay, so here are the 2 bumps outside, and my
I am
head's kind of the
scared.
middle bump. Okay,
This man, a bird, he's gonna.
nobody
lift
better
off.
be recording this. Wow, funny. Okay, so that's the way it's oscillating back and forth. And we can answer our question now as to, here comes the big question, yeah, ha. How big is the wavelength in this case?
1.5.
1.5.
1.5.
Okay, that's wrong.
Oh,
Okay.
nice.
0.6.
Let's use Finton here because I heard him there with the 1.5 and I like embarrassing Finton.
Oh,
0.6.
Okay, there was actually somebody coming in with the right answer, kind of. Who said 0.6?
I said 0.6.66 period
Okay.
or whatever.
Could we just call that 2/3?
Oh, that makes sense. Okay.
So if you look at this, the whole length is 1.5 wavelengths, and that's what Fintan meant. But 2/3 of the length is a wavelength. 2/3 of the whole length is the wavelength. And now things make a lot more sense because then we can say, aha, 2L divided by 3 is the wavelength. In this case, our third wavelength is 2L divided by 3. Now let's come back and think about our second wavelength. Our second length was L, but we could also call that 2L divided by 2. And our first length was 2L
Divided by 1.
divided by 1.
It is crazy.
Okay, and of course what this means is dot, dot, dot. We could also ask, what if we had this string and we had a large number of bumps?
2 hoch 2 ist was? Ist 4.
Okay, so this is the length L, and now we're looking at n bumps.
Sagen, Log 2 von 4. Und nicht Log 2 von 2.
Okay, Hagen, are you answering the question in German, which I think is cool? Was that you?
Wo mache ich jetzt die 4?
Somebody was on there talking German.
Also
Hagen's
das,
here.
das sagt 2, auf der rechten Seite wird es Log 2.
I'm not sure who's talking right now. Okay, the person solving math problems in German, is that what's going on here?
4 mal
That's Hagen's mic. I don't think it's Hagen though.
Oh, okay. All right, cool. So here we have n bumps, right? Here we had 3 bumps. I can even write that under there, 3 bumps. And now let's say we have n bumps. In that case, the wavelength would be, you guys can do this.
Also wir Log 2500.
Jetzt war
Okay, I turned Hagen's microphone off. I don't think he was trying to talk. Is that correct? Okay, so, all right,
Yeah.
good. So, so
2L over N.
2L over N, thank you. It was Konstantin, I think, right?
Yeah.
There we go. Cool, 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 cool. Make sense? All right, cool. Now, as we discussed earlier, for the sound there, we don't really care about the wavelength because we don't be talking about sound via the wavelength, right? We generally talk about light in terms of the wavelength, like we say red light is 400 nanometers, yes, 600 nanometers, or blue light's 400 nanometers, but we don't talk about sound that way. What do we use instead to describe what kind of sound it is?
The pitch, what, sorry?
Pitch or frequency, that's right. So when you
Okay.
talk about pitch, okay, or frequency, and that's a related property. So over here, we've got the lambda situation, the wavelength of each of these waves. And over here,
Wait,
we
is
have
there
a
a difference between frequency and pitch?
Okay, super. So pitch is how we describe in music or sound the frequency. It's kind of a casual word to say if you have a high voice, you have high pitch, but what that means is that sound has a high frequency in a technical fashion. So pitch is kind of the music term for the physical term frequency.
Okay.
So frequency and lambda are related through what equation? There's an equation that connects these two together.
Frequency times lambda equals speed.
Yes. Hang on. I think you said it wrong, Errol. So start with V. The speed of sound.
Speed of sound equals F times lambda.
Good. F times lambda is correct. Good. There we go. That's right.
Yeah.
I'm going to move this down a little bit here
Oh,
to make sure it fits. So we have that as the connecting relationship, Vs equals F times lambda. So that means for our case, F in this case, because lambda is 2L, right? That would mean F1, right? is equal to Vs divided by lambda. Does that make sense? Okay, I'll pretend you said yes. So this will be, now I'm leaving a gap right over here. Leaving a gap right here, Germans. Got it? Everybody okay with that?
Yes.
Okay, thank you for your enthusiasm.
Yes.
Really appreciate it.
Yes.
Then let's write down the F2 as well. Okay, the second frequency, again, the same idea. We have a wavelength. Now it's this one. And the speed is still the same. Okay, so it's Vs divided by this. Then we need to flip it. And watch this. Famous last words of skateboarders everywhere. I'm going to pop the 2 out front.
Can't you just do Vs divided by L?
I could, but I won't. And I'm going to write a 1 here. Why? We'll see in just a second. Okay? We'll continue down here, do the same thing, and you'll see a pattern. So then you'll see F3. Again, Vs divided by this pops around, leaves a 3 out front. Okay?
Okay, I'm starting to get it.
Okay, you guys seen the pattern?
I'm starting to.
F1 is 1 times that, F2 is 2 times that, and F3 is 3 times that. Make sense so far? And of course, that means in general, if we now had n bumps at the bottom, you guys can already, now it's not guessing, it's just kind of making a conclusion about what the nth frequency is that is present or can be present on such a string. Okay? Somebody want to just say it and we'll call on somebody, maybe somebody who doesn't talk as much. Panic is spreading through the herd. Hey, Felix is here. I'll mark him present. Just saw him show up. Cool. Oh, Henrik is here too. Hi, Henrik. Okay, and let's see if anybody else showed up who hasn't been here for a while. Not sure, but let's call on somebody to answer what Fn is. What's the equation we should write down? Let's call on Jasmine.
Oh. I think it's n divided by f Vs.
Mm-hmm.
Wait.
I think you're saying the right thing. You mean to say that?
Yeah,
I think.
that one.
N times that. Okay, super. That's correct. So it's n times this frequency, and of course that is the original frequency. Okay, so I've got it kind of covered up by my hand. So that's kind of silly. So what we really have here, I'm going to write it like this. That seems kind of dumb, but that's true, right? F1 is 1 times F1, where F1, the first frequency, this one, okay, we call this the fundamental. Oh, that's pretty, that red. I like it. I'm going to write out one out of space. We have to kind of go like this. Fundamental. This is the oh, crapperoo. So fundamental frequency. There we go. Vs over 2L is the fundamental frequency, also known as F1. Okay? And of course, what we see here is that F2 is twice that. Cool. Cool, 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 cool. 2 times F1. F3 is 3 times F1. And in general, it is true that the nth frequency is n times F1. We give those frequencies a name as well, and we name them after this number. Okay? Oh, now red's not good. Let's use a different color because I used red for the fundamental. Let's use green. 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 Good. 2, 3, 4. N. Okay? And these are the second, third, and then this is the nth harmonics. Okay? So twice the fundamental frequency is called the second harmonic, and the 3 times the fundamental frequency is called the third harmonic, and then of course n times the fundamental frequency is called the nth harmonic. Now, Two questions about that. One, why is it called a harmonic? Does anybody play an instrument? Does anybody sing?
And I used to play an instrument.
Okay, so when you sing or when you play an instrument, what does it, is there such a thing as music harmonizing, a tone harmonizing with another tone? Like if you sing,
Yes.
yes, okay, so certain frequencies work
Don't-
well together. Yes?
Okay.
Okay,
Yes.
yes, is that Ellie talking or who's it?
That is indeed me. Yeah.
Indeed, Ellie. So you agree that there are certain
Yes.
tones that harmonize, and that's indeed the case. So in this case, the second harmonic harmonizes with the fundamental because it has to, because the
Okay.
second harmonic, a reminder, is just the octave. Okay? F1 to F2
Oh.
doubles the frequency, so that is the
Oh, yeah.
one octave higher tone, and of course those harmonize. Two C's harmonize with each other. And now, ready for this? Well, let's think about the next one. Next one, we got F2 and F3. Yeah? F2 and F3 has a frequency ratio of 3:2. Do you guys know what two tones are called that have a frequency ratio of 3:2? You might have heard this word before. Konstantin?
Harmonizing.
I don't know what you just said.
Just harmony.
They do harmonize because that is called a fifth. You might have heard that before. Those two tones together form something called a fifth, and that harmonizes. It's F2 to F3 because they're in a ratio of 3:2. 2 plus 3 is 5, so that's called a fifth. Makes sense? I think it does.
Yes.
Okay, so we got the fundamental. We've got its octave one higher is F2, and F2 and F3 together are called a fifth because that's 2 plus 3. And we didn't write down F4, right? Which is the fourth harmonic. But the fourth harmonic, of course, is twice the frequency of the second harmonic, and therefore is again an octave to F2 higher, and that's 2 octaves higher than F1. Okay, so now we're talking a little bit about how music works and why things harmonize and why they sound good together, but that's kind of the idea. Now, I did want to add one question. We're almost out of time here. It's kind of weird that we call this the second harmonic, because what's the first harmonic?
Fundamental.
The fundamental. And it's kind of silly to call it the first harmonic because then you would be saying that the fundamental frequency harmonizes with itself. And that's of course like,
So it's unison.
duh, that's, we don't
basically.
say that. So, but still,
So it's-
we'll call this the second harmonic, this is the third harmonic, etc. Even though the first harmonic really doesn't exist unless you want to be switching to hyper nerd mode. Okay? Good. Now,
Okay.
the last wrap up we're doing is these are all the frequencies that can be present on this tone, on this string. But what's actually true is that several of these will be present at the same time. When you actually pluck this string, you will have a little bit of F1, a little bit of F2, a little bit of F3, and so on. And the specific composition of how much F1, how much F2, and how much F3, etc. are in that tone is different from type of instrument to type of instrument. So violin, different from cello, different from harp. But it's also different from the specific instrument that you might have to somebody else's violin. So if you have a violin, somebody else has a violin, they're not going to have the exact same mix of those fundamental with harmonic frequency mixes. And that specific mix is called the timbre, T-I-M-B-R-E, which is the how the sound sounds. How do you know when you listen to a guitar that it's a guitar? How do you know that it's a guitar string being plucked and not a cello string being plucked? Well, maybe you'd be like, I don't know the difference, but people who know music will be able to tell whether this is a violin or a viola. They can tell the difference. They can tell if it's a really nice instrument or not so great. Okay, so different mix, F1, F2, F3, maybe 13% of this, 20% of this, 33%. And if you have the recipe, and this is the last thing I'm saying today before we're closing things up, if you have the recipe of how much of each frequency you need to use to mix it together to make it sound like a violin, you could also synthesize the sound of a violin. Because if you know the recipe, you'll just tell a computer, why don't you play that much of this frequency, so and so much of this frequency, and another amount of this frequency, and we'll synthesize ourselves the sound of a violin. And of course, that's exactly what a synthesizer is, which today most people simply call a keyboard. Okay, so a keyboard that is a computer with basically a keyboard attached to it mixes these frequencies together to make the sound like it's a violin, cello, piano, whatever.
Can you move this down?
Move it down.
Yeah.
Cool. Okay. So we went slightly over. I hope that was somewhat interesting. I will take a picture of the board as well, and I will post it in the assignment for today, and I will post this recording as well. And I'm turning the recording off right now. And it is